The failure began at 0347 Central Standard Time on a Tuesday in October, not with alarms or visible warnings, but with a silent corruption in the pressure regulation subroutine of the city's master SCADA system, controlling 17 primary pumping stations across Chicago's water distribution grid. The system, a Siemens S7 1500 series programmable logic controller, networked to Schneider Electric variable frequency drives installed during the 2019 infrastructure modernization project, had been programmed to maintain distribution pressures between 65 and 85 pounds per square inch at street level, with automated adjustments based on elevation, time of day, and consumption patterns measured by over 8,000 flow sensors embedded throughout the network. At the moment of failure, a memory overflow in the pressure regulation algorithm caused the set point values to be reinterpreted as raw integers rather than scaled variables, effectively multiplying target pressure values by a factor of 10 and instructing the VFD controllers to accelerate the main distribution pumps to maximum rotational speed. The pumps, each capable of moving 12,000 gallons per minute at design capacity, began ramping up from their nighttime baseline of approximately 40% rated speed, their three-phase induction motors drawing increasing amperage as the VFD output frequency climbed from 24 Hz toward the maximum 60 Hz. Within the first 8 minutes, pressure readings at the Jardine water purification plant's main distribution header, normally holding steady at 78 psi, began climbing past 120 psi, then 180, then 240, exceeding the rated working pressure of the cast iron distribution mains installed in the 1920s and approaching the burst pressure thresholds of modern ductile iron and PVC service laterals. The SCADA system's alarm protocols, designed to trigger at pressure deviations of more than 15 psi from set point, had been disabled 3 weeks earlier during routine maintenance and not properly re-enabled, leaving the automated system free to pursue its corrupted pressure targets without human intervention or electronic safeguards. By 0415, pressure in the distribution system had stabilized at approximately 650 psi in the lower elevation zones of the loop and near south side, with peak pressures exceeding 800 psi in areas where elevation dropped below the pump station discharge elevation, creating static head conditions that compounded the already excessive pumping pressure. Residential and commercial plumbing systems in Chicago, like those throughout North America, are designed and code-rated for maximum working pressures of 80 psi, with pressure-reducing valves typically installed where municipal supply exceeds 60 psi. And these devices, mechanical regulators consisting of a spring-loaded diaphragm and valve seat assembly, began failing immediately when inlet pressures exceeded 400 psi, the point at which the spring compression reached its physical limit and the diaphragm material began to tear. The first structural failures occurred not in the ancient distribution mains, but in the newest residential towers along the lakefront. Buildings constructed between 2015 and 2022 with high-density polyethylene and cross-linked polyethylene (PEX) domestic water piping, materials chosen for their flexibility, ease of installation, and resistance to corrosion, but rated for maximum working pressures of only 160 psi at 73 degrees Fahrenheit. At 0422, a half-inch PEX supply line feeding a bathroom group on the 42nd floor of a luxury residential tower on East Wacker Drive separated at a compression fitting, the coupling body shearing away from the pipe as internal pressure overcame the mechanical grip of the stainless steel compression ring, releasing water at approximately 680 psi into the wall cavity between studs on a load-bearing shear wall. The water, under pressure nearly 9 times greater than a typical fire hose discharge, immediately began eroding the gypsum board interior finish and saturating the cellulose insulation, while simultaneously seeking paths of least resistance through electrical conduit penetrations and HVAC duct chases. The cascade of secondary failures accelerated between 0430 and 05 as the high-pressure water found pathways through building envelopes that had never been designed or tested for such hydraulic loading conditions. In the tower on East Wacker, water emerging from the failed PEX connection traveled horizontally through the wall cavity until encountering a vertical plumbing chase, where it fell under gravity while simultaneously being propelled downward by the continuing pressure of the municipal supply, creating a hybrid flow regime that combined characteristics of freefall and pressurized discharge. Within 12 minutes, the water had descended through 17 floors, saturating fire-stop materials at each floor penetration, compromising acoustic insulation and pooling above suspended ceiling systems until the weight of accumulated water exceeded the load capacity of the ceiling grid suspension wires, typically rated for 10 pounds per square foot of distributed load, but now supporting localized loads exceeding 60 pounds per square foot. The first ceiling collapse occurred on the 38th floor at 0434, releasing approximately 400 gallons of water into a 3-bedroom condominium unit, the water spreading across the engineered hardwood flooring at a depth of approximately 1 inch before finding the gaps around the unit entry door and flowing into the common corridor. Similar failure sequences were occurring simultaneously in 47 other buildings across the downtown core and near north neighborhoods, each following the same progression from initial pipe or fitting failure to wall cavity saturation to ceiling collapse to horizontal spread across finished floor surfaces, the rate and extent of spreading determined by floor levelness, door clearances, and the location of elevator shafts and stairwells, which acted as vertical conduits for water transmission between floors. The structural integrity problems became critical after 0530 as accumulated water weight began affecting load-bearing elements and mechanical systems that had never been calculated to resist sustained hydraulic loading. In buildings constructed prior to 1960, when concrete floor slabs were typically poured directly over corrugated steel decking without waterproof membranes, water penetrating through ceiling collapses on upper floors began seeping through the concrete itself, a process accelerated by the existence of shrinkage cracks and the porosity inherent in concrete with water-cement ratios above 0.45. The water, emerging from the underside of floor slabs as a fine mist of droplets, created what structural engineers term a rain-loading condition in the floor cavity below, saturating any fibrous insulation present and adding dynamic loading to mechanical and electrical systems suspended from the structural deck above. In the older buildings of the loop, where floor-to-floor heights often exceeded 12 feet and ceiling cavities contained decades of accumulated infrastructure, cast iron soil stacks, copper water lines, galvanized steel conduits, and HVAC ducts wrapped in asbestos-containing insulation, the added weight of water saturation began exceeding the capacity of the original hanger rod and strap suspension systems, many of which had been installed in the 1920s and 1930s, using materials and connection details that predated modern structural codes. At 0547, in an office building on South LaSalle Street constructed in 1927, a 4-inch cast iron soil stack that had been conveying wastewater from upper floor bathrooms for 96 years separated from its hanger supports when the steel strap attachments corroded through under the combined stress of original pipe weight, water saturation of surrounding insulation, and vibration induced by the abnormal flow velocities in nearby water supply lines still operating at 700+ psi. The water hammer phenomena began manifesting throughout the distribution system after 06 as the extreme pressures created conditions for rapid valve closure events and pressure wave propagation through the piping network at velocities approaching the speed of sound in water, approximately 4,800 feet per second in steel pipes. Water hammer, a pressure surge or wave resulting from a sudden change in fluid velocity, occurs when kinetic energy in moving water is converted to pressure energy by rapid deceleration, typically caused by fast-acting valve closures, but in this case triggered by the catastrophic failure of pressure-reducing valves, backflow preventers, and fixture supply stops throughout the system, each failure creating an instantaneous flow stoppage that generated a pressure spike traveling both upstream and downstream from the point of closure. These pressure waves, with magnitudes calculated using the Joukowsky equation and reaching peak values of 1200 psi or more when the baseline pressure already exceeded 700 psi, propagated through the distribution mains and service laterals at acoustic velocity, reflecting off dead ends in closed valves and creating standing wave patterns that imposed cyclic stress on pipe walls, fittings, and thrust blocks. In areas where the distribution system included significant lengths of unrestrained pipe, meaning pipe sections not anchored at bends and tees with concrete thrust blocks designed to resist the hydraulic forces generated by changes in flow direction, the pressure waves created net forces sufficient to cause pipe movement and joint separation, particularly at mechanical joints in ductile iron pipe, where the only connection between pipe sections consisted of a rubber gasket compressed by the weight of the pipe and soil above. At 0623, a 12-inch ductile iron distribution main installed in 1998 beneath West Madison Street separated at a mechanical joint near the intersection with North Halstead Street, the bell and spigot joint pulling apart under the combined effects of water hammer pressure spikes and inadequate thrust restraint, releasing water at an initial flow rate estimated at 3,200 gallons per minute directly into the sandy clay soils of the Chicago Lakebed Formation. The subsurface failures created secondary hazards as water at extreme pressure encountered soil conditions ranging from competent clay to loose fill material, the hydraulic gradients sufficient to initiate internal erosion and piping failure in cohesionless soils, and to hydraulically fracture clay layers along existing planes of weakness, such as desiccation cracks and root channels. The water escaping from the separated joint on West Madison Street, initially flowing at pressures near 680 psi, despite the elevation head loss associated with the depth of the pipe below grade, began eroding the surrounding soil matrix, creating a void space that expanded radially from the pipe at a rate controlled by the erodibility of the soil and the magnitude of the hydraulic shear stress at the soil-water interface. Within 15 minutes, the void had expanded to a volume of approximately 800 cubic feet, equivalent to a sphere with a radius of nearly 6 feet, and the loss of soil support beneath the pavement structure initiated a subsidence event that manifested at the surface as a depression approximately 12 feet in diameter and 2 feet deep, the asphalt pavement initially sagging and cracking in a radial pattern before failing in shear and collapsing into the void below. The water, no longer confined by the surrounding soil, began surfacing through the pavement breach, creating a fountain discharge that reached an initial height of approximately 18 feet, the trajectory and height determined by the discharge velocity calculated from the Torricelli equation and modified by the effects of air resistance and the turbulent breakup of the water jet into droplets at elevations above 3 to 4 feet. Similar subsurface failures were occurring at 17 other locations across the city where distribution mains had separated or ruptured, each failure following the same sequence of joint separation or pipe rupture, soil erosion and void formation, surface subsidence, and ultimately fountain discharge or surface flooding as the water found a pathway to open air. The effects on building mechanical systems became catastrophic after 2007, as the sustained high pressures caused failures in fire protection systems, HVAC equipment, and emergency backup systems that had been designed to operate within narrow pressure ranges. Fire sprinkler systems, designed for maximum working pressures of 175 psi and incorporating heat-activated fusible link heads rated to open at temperatures between 135 and 165 degrees Fahrenheit, began experiencing structural failures of the sprinkler heads themselves, the brass or bronze body castings fracturing under hoop stress that exceeded the material's ultimate tensile strength of approximately 40,000 psi when wall thickness was reduced to the minimum values used in modern sprinkler head manufacturing. The failures occurred not at the fusible link, which remained intact and unheated, but at the thread interface between the head body and the branch line nipple, where stress concentration at the root of the threads and potential metallurgical defects from casting created weak points in the structure. When a sprinkler head failed, it released water at the full system pressure of 700 plus psi, creating a discharge flow rate of approximately 180 gallons per minute from a single half-inch orifice, compared to the design flow rate of 25 gallons per minute at normal system pressure. And this seven-fold increase in discharge rate overwhelmed floor drains, created indoor flooding conditions measured in inches per minute, and imposed dynamic loading on floor structures from the momentum flux of the high-velocity discharge. In a hospital on the near west side, the failure of 12 sprinkler heads across 3 floors released over 2,000 gallons per minute into critical care areas, patient rooms, and pharmaceutical storage spaces, the water depth reaching 6 inches in some corridors within 10 minutes of the initial head failure, and creating electrical hazards as the water encountered floor-mounted electrical outlets and medical equipment power supplies. The failure of pressure relief and safety systems throughout the affected area revealed fundamental assumptions in infrastructure design that had never been tested under such extreme conditions. Pressure relief valves installed at critical points in the distribution system, devices intended to automatically open and discharge water when system pressure exceeded safe thresholds, were sized and set based on the assumption that overpressure events would result from pump failures or valve operation errors that might create pressure spikes of 20 to 40 psi above normal operating pressure, not sustained pressure increases of 600 psi or more. The relief valves, typically spring-loaded poppet valves with discharge capacities of 50 to 100 gallons per minute, opened immediately when pressure exceeded their set points, but the discharge capacity was entirely insufficient to relieve the pressure being generated by the 17 pumping stations operating at maximum speed, and the sustained discharge at pressures far exceeding the valve design pressure caused erosion of the valve seat and disc, rapidly degrading the sealing surfaces and converting the valves from controlled relief devices into uncontrolled leak points that discharged water continuously without providing any meaningful pressure reduction in the system. Similarly, the expansion tanks installed in closed-loop heating and cooling systems, designed to accommodate the volumetric expansion of water due to temperature changes by compressing a captive air charge separated from the water by a flexible diaphragm, were subjected to pressures that exceeded the burst rating of the diaphragm material and the structural rating of the steel tank shell, resulting in catastrophic tank failures that released the entire water content of the closed-loop system, plus whatever additional water had been forced into the system from the municipal supply through failed makeup water valves and backflow preventers. The human discovery of the failure began gradually after 0630 as residents and early shift workers encountered the first visible manifestations of the infrastructure failure, most commonly in the form of water discharging from light fixtures, appearing as seepage around door frames, or emerging from electrical outlets in walls adjacent to plumbing chases. But the distributed nature of the failures and the lack of any obvious external cause led most individuals to interpret what they were seeing as localized plumbing problems rather than symptoms of a system-wide catastrophe. The first emergency call related to the failure was logged at 0642, a report of water dripping from a ceiling light fixture in a fourth-floor apartment in Lakeview, and over the following 30 minutes, 911 dispatchers received an additional 127 calls reporting water problems, flooding, ceiling collapses, and fountain discharges in streets, but the volume and geographic distribution of calls did not immediately trigger recognition of a common cause, and initial emergency response consisted of dispatching fire companies to individual addresses to investigate reported water problems using standard protocols for burst pipes or plumbing failures. The first indication that the failures might be related to abnormal system pressure came at 0718 when a Chicago Fire Department battalion chief, responding to a report of flooding in a high-rise on North Lakeshore Drive, used a handheld pressure gauge to measure the static pressure in a standpipe hose connection and obtained a reading of 740 psi, a value so far outside normal ranges that he initially suspected gauge malfunction and requested a second gauge, which confirmed the reading. At 0731, the battalion chief transmitted a radio message to the Chicago Office of Emergency Management and Communications reporting abnormal high pressure in the city water system, multiple buildings affected, recommend immediate contact with Department of Water Management. And this message initiated the first official recognition that the city was experiencing a systemic water infrastructure failure rather than isolated plumbing problems, though by this time the failure had been propagating through the system for nearly 4 hours and had already caused structural damage to over 200 buildings and created 23 active street flooding sites from main breaks. The process of regaining control of the system extended over 17 hours from the moment of first official recognition to the restoration of normal pressure set points. Complicated by the distributed nature of the SCADA architecture, the lack of manual override capability at individual pumping stations that had been designed for fully automated operation, and the need to isolate and drain portions of the distribution system to locate and repair the software fault in the master controller without triggering additional pressure transients that might cause further damage to already stressed infrastructure. The immediate priority was reduction of pumping station output, achieved initially not by correcting the software fault, but by opening a series of large-diameter isolation valves that allowed water to bypass the distribution system and discharge directly into the Chicago River, a crude but effective method of pressure relief that began reducing system pressure at 0815 and achieved pressures below 200 psi by 9:30, though this remained more than twice normal operating pressure and continued to cause fixture failures and minor pipe breaches in buildings throughout the affected area. The software fault itself was identified at 11:45 by a control systems engineer from the SCADA vendor who had been summoned to the Department of Water Management's central control facility, the investigation revealing that the memory overflow had resulted from an accumulation of uncleared alarm flags and a buffer that should have been reset during the maintenance procedure 3 weeks earlier but had been overlooked, the buffer eventually filling completely and causing a pointer overflow that redirected pressure set point reads to an area of memory containing raw sensor values rather than processed control parameters. Correction of the fault required uploading modified firmware to the S7-1500 controller, a process that necessitated taking the master controller offline and switching to manual control of all 17 pumping stations, with operators at each station receiving verbal instructions via radio to set VFD speed references to specific percentages based on zone pressures reported by field personnel reading mechanical gauges at key points in the distribution system. This manual control regime continuing until 2035, when the firmware update was completed and the system was returned to automatic control with verified set point values and restored alarm functions, at which point system pressure was gradually reduced to normal operating ranges over a period of 2 hours to avoid creating negative pressure transients that might cause backflow contamination or column separation cavitation in high elevation areas of the network.